I'm Beth Harrison-Meyer, SVP of Global Marketing at Aptyx, and I will be the moderator for today's discussion. We're going to look at complex catheters from the lens of extrusion because it's foundational to the catheter system. And in particular, looking at how early decisions and the interaction between those decisions impacts performance and manufacturability, and ultimately the ability to deliver a high-value, high-quality device. And if you've ever had a program that looked right on paper, and then you got to validation, and it failed or something went wrong, you're not alone, and that's what we're going to talk about today. So to help me unpack that, I have a team with decades of experience and who look at this from different perspectives. Patrick Daly has worked across complex extrusion and catheters from virtually every touch point and really sees how early design decisions impact performance. Perry Cicalis leads development and manufacturing for precision extrusion here locally in the Boston area in Taunton. And he really sees where programs hold up or where they don't when they scale. And then Joe Nasuti works closely with customers and in other areas, but he's really seen where teams have disconnects between expectations and reality. So guys, I'll let you share a little more about your backgrounds.
Thanks, Beth. I'm Patrick Daly, Global Director of Extrusion for Aptyx. I've worked for over 20 years in the medical device space for companies of Tactics, which became Kurgana Tactics, Optinova, to name a few, as well as Biomerics. I've been at Aptyx now for about a year and a half. And, one thing that really drives me for, catheter performance as well as extrusion and how critical it is that patient care is always like the most important thing. And these devices that we do can save lives. So that's very important to me. And that's why I'm passionate about the medical device industry.
Perry?
I'm Perry Cicalis. I'm the Chief Operating Officer for Aptyx Precision Extrusion here in Taunton. I'm married. I have 3 kids and 2 grandchildren. I'm a plastics engineer. I got a degree from UMass Lowell quite a while ago. I've been involved in extrusion for almost 40 years. I've been an entrepreneur for 30 years, and in about the last decade, I've been involved in creating a precision center of excellence for medical tubing here in Taunton. Now that we've joined up with Aptyx, we're making a bigger impact on really moving that center of excellence forward. Love to see some of you come look at what we're doing and what's new in Taunton, just give us a call, and would love to show you around. It's very exciting.
I'm Joe Nasuti. I'm the VP of Sales at Aptyx Precision Extrusion, working alongside Perry. Also a graduate from UMass Lowell for plastic engineering several decades ago. And I've worked in materials for many years. I've worked with injection molding. I've done tech service, but for the last 28 years, first with Argos and now with Aptyx, been heading up the extrusion sales. And we've seen a lot of different things, and this is a great talk that Beth has pulled together. So we look forward to this.
Thanks, guys. It's a great experience. We would very much like this to be a conversation. As Jim said, he will have the mic. Questions are welcome. We have time at the end, but really always open for questions. And before we dive into the heart of it, I'll share a brief, and I do mean brief, overview about Aptyx. So at Aptyx, we support medical device development and manufacturing. We bring a very broad set of capabilities to bear for our customers, working anywhere from components to finished devices, from design development to full-scale manufacturing. But what makes Aptyx is the team. It's the make-it-happen mindset. Our team loves nothing more than diving in, partnering with customers, solving complex challenges, and really looking at where early design decisions impact manufacturability. And that's what we're going to focus on today. So when we look at catheter programs, many teams think that the biggest risk or challenges happen later in verification or scale up. But that is not where they start. The issues that slow programs down and add cost and risk already built in the early design stages, and often before teams understand the impact of those decisions. And if they're not well understood, it can be several months later or longer than that in validation when they show up, and we get to those four-letter words again: time, cost, and risk. So that's what we're going to unpack today. Modern catheters are increasingly complex, more materials, more advanced materials, tighter tolerances, much more integration. In fact, really more like systems than a group of components. And Patrick, you've talked about that before.
Yeah, I think one of the new things is that tubing is no longer a secondary component. You know, it directly influences how the device performs, and you know that's how it directly goes right from the extrusion point. So your materials, design, and everything like that influences each other.
So more than a component, impacting performance, and I think what's really important at the end of the day, very few of us get judged on the performance of a single component or one thing we do. We get judged on the impact of the system. And if the system is a catheter, or really virtually any other medical device, there's a patient at the end, so that performance is critical. And looking at timing a little bit more, again, this is where we see that disconnect. When you look at the top bar, further along in development and into validation, that's where many people think the biggest risk are, where the problems are showing up. But that is, again, not where they are starting. The things that show up in validation were built in much earlier in that early design phase. That is where performance is getting defined. So Patrick, what gets defined here?
Yeah, this is where you're really defining the extrusion profile, your tolerances, your shape, geometries, how many lumens, and materials. And I think one of the challenging things is that these decisions may seem like they're coming early, but it is very important that we deep dive into those decisions before we assemble the catheter.
So the early phase is critical. We're making decisions earlier, then why are things still happening later?
I think it's because, performance isn't really driven by a single factor. Everything kind of influences everything. Extrusion will influence the materials. The materials will obviously back and influence the extrusion. The manufacturing, secondary ops, assembly, the tolerances, they all influence each other. And that's what we're seeing. And that's why, getting these decisions made in the early stages is the most important.
Yeah, and just to add to that, I really agree, but you look at an entire system, and then if you start diving just a little bit lower, you see that the tube is the building block of that. And the geometry of that is very important, and then even beyond that, how is it manufactured, what goes on, and it can impact everything in the system.
And yet we'll be the last ones that they'll contact. They've got all the other components mapped out and designed, and we get the phone call, and it's like, we just want the tube, and we just have to let them know that when we get the tube to them, that there's going to be interactions, as Perry mentioned, that they did not anticipate, and those are things that we want to address early on, and early to make sure that that's something that isn't going to manifest itself into a bigger problem.
And I think you've said, too, when these problems tend to show up later, people think it's a manufacturing issue.
They often do, yeah. Something will happen, and where there's a failure, a leak or something, and they think it's just manufacturing, when in fact it was design that could have been addressed much more easily if it was looked at earlier on.
So everything interacts, and that's driving performance, common theme. But it reminds me of an analogy we've talked about, building a race car, or really any car.
Yeah, I think any car would be a good analogy, how every little component of the vehicle helps it perform. So your steering column, your drivetrain, and everything like that could affect your alignment down the road. So something similar to that is like how your catheter should be considered in the design steps.
And for a layperson like me, vehicle alignment is one I understand, because we're saying something early can show up late. And perhaps when you get at speed, and I would imagine about everybody in this room has been in a car when the alignment was off and it's shaking, and clearly that's not what we want to have happen with the catheter, or if you were here for the last session where they were talking about stroke and super advanced procedures with those catheters. So the good news is that it's not coming from everywhere, these challenges or areas you need to hone in on. There are 3 key areas, and we will take a closer look at those. Not a super deep dive, hitting on what's most important, but certainly very available to talk later as needed. So design, Patrick?
Yeah, I mean, this is where the lumens get defined, your geometry and materials. That's the most important part of the system, and it kind of directly influences how the system behaves.
And manufacturability?
Well, you have to take everything into account, including materials and that impact. When those come into a system, they have a larger play. So there's simple things like orientation or molecular weight that can create variations in the product during the processing. So there are impacts from everything. Materials obviously are a big deal in that as well.
Yeah, I mean, materials are going to drive some of the properties in addition to the design. And when you look at the materials, people know what they know, but there's so much more out there. They know they want a 70A durometer, but they're only familiar with that in, say, a flex PVC. And they don't know how torqueability is going to be different if it goes to a TPU or some other thermoplastic elastomer. And the durometer itself, is that at room temp? Is that at body temp? How do things change? And in the fillers, we work closely with our vendors. We're making extrusions on a daily basis, and the catheter builds for the OEM. They're looking at one product over many months or even years, so they don't have the same relationship with the vendors that we would have in terms of what additives are going to work for the materials, and how that affects the properties and everything else, down the list as the design goes on.
So we focus in on these 3 areas, but it's important to note that they are not independent. They all interact. And let's take a deeper look at design.
Sure. Looking at the profiles that you see here, you have multiple different multi-lumen segments. So, each one of those lumens is designed to either keep something separated or, for air or flow or irrigation, or maybe even putting a camera down or whatever the device is for, whatever procedure. So taking a look at that, you see how you have your septum walls. You know that you can't have any crosstalk between your lumens. You don't want any sort of thinner walls coming down. You want to keep them uniform throughout the extrusion. It's very important that happens, because if you have, let's say you have an instance where you have to maintain a burst pressure, if you blow out one of those sidewalls, you're going to have failures later on down the line, and that's going to be crucial to how your device performs.
So I'm looking at the same pictures you guys are looking at, and those are fancy tube, with the lumen designs and whatnot, but even the simple tubes can be complex.
That's very true.
Well, these are more simple than the one we were showing even, though. But
Also true.
Yes.
I mean, if you look at the detail in those pictures too, you'll see that there's variations in the wall thicknesses, as well as the distances between all the lumens, and that goes back into what we were talking about, material choice and the ability for the polymer to flow through those areas, because they become restrictive areas or high flow areas. So we have to work on that to make these tubes come out round and do that every single time.
so what you're saying is the complexity is not always where people expect it to be.
Yeah, absolutely.
A little bit like life. So I assume that continues as we look further at materials and manufacturability. Joe, you want to talk a little more about materials?
Yeah, I mean, as Perry said, as you're looking at the the septum walls, or anything that's on there, when we're extruding, the first shot out of the gate may not be exactly in spec, so you have to tweak it, and then the customer will get it, they'll test it, and they'll say, oh, can you go thinner here or thicker there? And they're not looking at the complexity, because every material or most materials will behave differently as you get thinner. You're going to be, aligning the molecules in a different manner and getting different properties. And then we want to see how the fillers are going to, perform during that same sequence, where something's going to get thicker or thinner. And these are all things that we want to look at over a range in order to provide the best product, right out of the gate, and give them something that they can work with for whatever's going to be done to that tubing after they receive it.
What about like a complex material, like let's say a polyurethane-based resin that has different melt flow indexes with different batches? And how do you combat that, like for validation? Like what's some of the things you do? Because you can't have the temperatures have to be at plus or minus 20 or 10 degrees if you validate by temperature, but now you get a batch of resin that has a melt flow index of 2 when you validated your last one at maybe a 12. So what would you do in that situation?
Well, then that's a loaded question.
I know.
Anybody that's run TPUs in any significant volume has known that even within the same bag, sometimes you'll get different viscosities. If you were going to perform a melt index on one end to the other, it can change pretty dramatically. So in the case of a validation where we have to come up with a robust process so we can make this into a manufacturable product, we won't look at just, melt index or the viscosity of the material. We'll look at how it's processing, for instance, with the TPUs in particular, at pressure. So we'll define a head pressure that provides us with a good product. And we have a range that we would run through a validation. And that pressure is something that we can chase during the processing. So we might have to go lower on the temps than we would expect to have to go, or higher as it may be, to zero in on that head pressure, which will actually bring that viscosity into a range to be able to produce the part.
Yeah, so processing characteristics are going to be manipulated in that case around that control point. Realizing that there's a stack up everywhere is, we haven't even talked about secondary operations if something needs to be printed on, and we add a lubricious additive to the material that can lower the surface energy and also change the way the material flows through the tooling. So knowing those things up front and the impact of those things, and talking with the design teams, no matter how far down the line, what their needs are, is an important thing.
So a lot of factors to consider. And there's one I've heard you say before that you've drilled into my head. A data sheet does not equal performance.
Yeah, the data sheet. It's a loose suggestion from the manufacturer of the material, so they don't get caught. Providing something where you get different properties once you make it. It's a laboratory number. It gives you a ballpark of where it's going to be. Something as simple as durometer, which I think we talk about a lot here because of flexible tubing, but durometer how? I mean, how's it being measured? Instantaneous, delayed readings, and then when you get it onto a tube, now it's a round product. Are you measuring directly on that? So they're guidelines. They're important. Data sheets, obviously serve a purpose, but they're not the end all when it comes to knowing which material is going to perform a certain way.
I mean, also with materials, over-engineering can be a problem as well. Sometimes we find out later in a project there was a cost point, and customers might be not want to share that with us on what they need to keep a cost in. So choosing a TPE over a TPU in a situation where it might be functional for that product is something that should be brought up early too, so that you can get some advice from a team that might have used it in a similar application or just has some other options for you material-wise.
So clearly, quite a lot of elements to consider. So when we get into the full-scale builds and we see things happen, so much of that is due to earlier decisions, as we're saying. Can we walk through a couple of examples?
Well, one of the biggest examples of scrap and problems with catheter design is delamination. And so you have your stack-up tolerances. A lot of the times the extrusion is the one part that you can adjust. You can't adjust your braid wire. You can't really adjust the pitch of your coil or your thickness of your wire. So you have your extrusions, right? And so With delamination, what can happen there is your outer layer does not adhere to your inner layer, and there is braid, coils, or now we're seeing a lot of laser cut backbone technology where a hypotube is laser cut to have flexibility at one end and stiffness at the other. And so we have to kind of make our extrusions rigid and flexible to make that whole intricate piece work. And so when the layer from the outside doesn't adhere to the inner layer because there's too much braid or there's too much coil pitch or not enough gap in your laser cut backbone, the catheter will delaminate and each layer will peel away from each other. And depending on your order of operations, you will have to scrap the entire piece. And that could be marker bands, that could be an overmold. I mean, it depends on where this shows up. So it's a very important part to make sure that does not happen in your design. And that, that going back to talking about what we've been saying earlier is that bring us into the design early. And, these decisions, we can try to combat this problem, so.
I can offer up a simpler example as well. We were brought into a job recently where there was a design freeze, and we just figured out we make parts, we send them to the engineering team, they tested them, everything looked great. We moved into validations, and everything worked out fine. We were our 6 lumen profile was perfect and was sent out fully validated as a tube. Once it got to the assembly team that our customer had, they started seeing problems in the assembly where the product was leaking, and none of this was seen during the initial work. So we had to go and look back at that and find out why that was happening. And we came to find out after a lot of research and a lot of testing that it only worked in 60% of the tolerance range. So we had to go back. We probably lost 6 to 9 months on the project. It sounds like it wasn't a big deal to go find this, but by the time you go through all the work and the retesting, and we were able to do that. It also increased the cost, obviously, of the project, but the cost of the product, because we had to the only fix without going through a full design change was to reduce the tolerances. Fortunately, we were able to do that, and the project moved forward. But it was a slowdown of quite amount of time and more costly in the manufacture of the product long term for the device.
Yeah, we all remember that job. But as Perry said, it's just looking at the whole picture, and from our perspective, the tubing, and how it interacts with all the other components, it's critical to prevent problems down the road. That was literally that was a very easy way that we could have saved, like you say, 6 to 9 months. I think it was a little bit longer than that.
I think it was just the discussion with the full team early on.
Yep.
The assembly team, I think, was left out of it because it was assumed it was going to work, and I think their input earlier might have solved the problem. I mean, yeah.
I mean, it was so it was a molded part that the tube got put into where they found the leaking. So it was a molded component that passed all validations, and it was an extruded tube that passed all validations, and then it failed. So you really do have to look at everything at the whole thing to better understand what the interaction is going to be.
Yeah, that's a great example of the impact of the overall system. And when these challenges happen later, teams really feel it in time, cost, and risk. Again, those 4-letter words. But it is not inevitable if decisions are made earlier, if teams, emphasis here on the word teams, are brought together earlier, you get the right perspectives around the table, it can be very different. So we've shared a couple of negative examples. Be a good time for a positive one.
Sure, I can talk about a win. There was a microcatheter we worked on collaboratively with another partner, and it was an O26, so a 26 thousandths OD max, so very, very small. Had to have a 14 thou guide wire in it. Also had to have multiple different materials with a braid pick count of I think about 16 picks per inch. So we were able to design this catheter from the beginning. We knew what materials worked well together. It was a polyethylene to PBAX. So you had an inner layer of a lubricious additive with PBAX, and you had polyethylene over the top. And so, with all the decisions that were made up front, working collaboratively with the team, it's a successful product that's on the market today, and I'm pretty proud of that. So,
Well, that's what we're aiming for, especially with patients at the end. But what's interesting, that was the most complex example, but it was the positive example. Now, obviously, we're choosing what to share, but what it comes back to is not so much the level of complexity, but the way the problem was approached. So instead of fixing surprises later, they were engineered out early, and you built something that lasts and help patients.
yeah, that's exactly right.
Well, and that's what we're all aiming for. So if there's one thing you take away from our discussion today and how to avoid these challenges, is to ask better questions earlier, and we have 3 we would suggest. So first, how will this behave as a system? Patrick?
Yeah, just make sure you don't evaluate, one piece in isolation. Evaluate how the whole system will work. Take that into consideration, and that'll lead to success.
Yeah, and in manufacturing, it's just understanding that the processing of the polymer is going to have an impact on everything as well. And there's a stack up of all these things that come in. It's easy to look at that complex catheter build, but then when you're going into the extrusion, there's so many impacts in the process and the material selection, those things that come into play. We've got a great team of engineers at the Taunton location that have taken on a lot of these challenges. So, we have a lot of experience here, but there's a lot of other good people that are there that can help with questions all the time too.
And then the third, downstream interactions.
Yeah, the downstream, anything that's going to happen after we make the tube, or whatever, how far we take that component. Perry mentioned an example, oh, by the way, it needs to be pad printed, and it was a lubricious additive that did not allow for that. It lowered the surface tension on the product too much. Knowing that up front helps. How is it going to be sterilized, or if it's going to be sterilized? Are you going to encounter a color shift with the material? Is it going to run through a temperature that's going to change the parameters of the tubing, maybe change dimensionally if it's a higher temp sterilization process? Everything like that just plays into a role of, it needs to be addressed on the front end so you don't have to worry about it afterwards.
And, just to add, even if you don't know the right questions, just getting the conversation going is important. Joe's great at asking a million questions about what this material or what needs to happen with this device.
Or whoever your partner is. At the end of the day, communication, collaboration is going to serve all of us well, whether it's catheters or really anything. But here we're talking about how it's very important to get the design right, but more than that, you need to know what will happen next, and you need to understand the system or work with people that as a team can do that.
Yeah, and I think, medical tubing, you can't approach it as a commodity anymore. It's very important to get those designs correct, and, the engineered structure of that, it absolutely needs to be talked about up front, as, it's a very important part of the catheter process, so.
It's foundational to the system, and I think what we're saying is to really look at the system. And to close it out, I want to bring it a little bit full circle. If you were fortunate enough to be at the Women in MedTech breakfast this morning, Dr. Carla Perron, who's the Chief Medical Officer from Philips, gave a great talk, but she had a recommendation that I think applies really well here. And she said that, to quote her, we need to rethink, do we know everything when we are designing for reality? So again, it's about getting those right perspectives. And of course, thinking about the patients at the end of the product. And with that, we will open it up for questions. Would love to hear your challenges. Please challenge this team, I beg of you. Also, you can download the presentation at the QR code. Our emails are there. Anytime, we're happy to talk. No questions or no strings attached. So.
For all the technologies that we cover at Medical Design Outsourcing and DeviceTalks, when you see the fastest growing areas like TAVR, pulse field ablation, renal denervation, I mean, the list goes on and on. We're reaching further into the body with advanced sensors and new ways of delivering therapies. It really is incredible. So thank you for the work that you do. Everyone out here, I could ask questions all day, but I'd like to get some questions from the audience. This is my favorite part. So if you want to put your hand up, I will run as quickly as I can to you, and we can ask some questions. So here you go.
Thank you. Great presentation. I really enjoyed the conversation that you all had. Just thinking about really early stage and being involved with human factors and being involved in developing the use case and all that, how frequently are you getting involved that far up in user needs definition?
Our team in Charlotte that works from design development to full-scale manufacturing is highly involved in that, and from the extrusion to really all factors of the catheter.
Yeah, I think one of the things we like to get into right away is the fit form function of the device. You know, making sure that we don't think about tolerances at first. We have to understand what it needs to do, what it's designed for, and what the purpose is. So yeah, as Beth said, our team in Charlotte, full-scale catheter manufacturers, years and years of experience, as well as our Taunton facility has a lot of years of medical device as well. So you know, we try to get in that early stage as best as we can, and we're seeing more and more collaborative efforts between ourselves and our partners.
And in particular in Taunton, the precision extrusion, division of Aptyx, we're a fairly newly acquired entity. Prior to that, we did, 27, 28 years as Argos, and too often we were just an afterthought, not us, the company, but the tubing itself. Since the acquisition of Aptyx, different sales force, bringing in different OEMs at different levels, we've been fortunate to have a significant increase in improvement in terms of being further along, seeing more of the whole picture on the front end. And that's been very, very helpful, and I think that's kind of what drove the topic for discussion tonight, because we see how beneficial it can be, and how detrimental it is when that's not when it doesn't happen like that. Thank you for your question.
Yeah, great question. Thanks so much. Any other questions? I actually have one based on in the conversation. There's a bit of a snicker and some murmurs coming up from the audience about materials data sheets. And I'm wondering if you can talk about where do you see the biggest gaps between the materials data sheets and actual real-world extrusion performance?
Well, I mean, a good example is tensile strength. And if you're looking at very common material that we use is TPUs, we'll first of all, if the data sheet is probably based on either a molded or a compression molded plaque with a dog bone cut out of it. And we're extruding a tube, so we're aligning the molecules a little bit differently. And so we'll get different properties to begin with. But from our perspective, if we have to meet a minimum requirement, the properties change after 24 hours. So we can't even measure it and know that what we're making today is going to meet the requirements per specification if they dial it in too tightly based on a data sheet. So, I mean, that's just, one example. There are other properties that have, will behave similar to that. But, I mean, it's just something that, you got to look at as a guideline. Try not to throw it in as a minimum. And again, the data sheets say it in the tiny writing at the bottom from the material guys. It'll say not to use it as a specification, but too often that's ignored, and we have to intervene and say, no, you can't do it like that.
Yeah, just to add to that, there's again going back into the processing. In order to create some of these complex tubes, you have to use high drawdowns or something mechanical to overcome something, whether it's air or vacuum. And you may have to change your dye to tank distance or water temperatures and material temperatures. And again, the way the material forms, that can affect crystallinity in a PBAX or nylon-based material, and that can change some of the properties also that are listed. So there's those types of interactions as well that have to be considered.
Any other questions? Oh, here we go. While I'm on the way, we're always talking about trade-offs in engineering at MDO, and I'm wondering, can you talk a little bit about some of the trade-offs between lubricity and mechanical performance?
Well, not always a trade-off there. It depends which mechanical performance we're talking about. Any additive is going to potentially impact the mechanical performance. Lubricity, it really is, how does it manifest itself? Everybody has their own secret foo-foo dust to put in to achieve lubricity. Whether it be a siloxane or anything that they have that's just listed on the MST sheet as proprietary. The level that it's in there and how it works itself to the surface. Is it semi-compatible and wants to work its way to the surface, or is it integral to the polymer chain after the processing? And does it have an effect? Well, the goal is whenever you're putting an extra ingredient, an additive into a compound, is to not negatively impact the mechanical properties. But that is something that whenever, because we'll run natural or clear, materials that have no additional additives, and as soon as you start adding something as simple as barium sulfate, never mind a lubricious additive, you know that you're going to have to start paying attention when you're dealing with very, very thin wall extrusions. But it's not a one-to-one interaction. You have to look at them individually.
We're also seeing a shift. I've seen a lot of research and development projects come in lately that have shifted from PTFE lubricious liners to start your catheter builds. We're using more like 72D PBAXs with lubricious additives that are added to them from a couple different compounders that we use, and we're not able to achieve the coefficient of friction exactly to the PTFE what it is, but we're seeing that we're able to build some catheters right now in early stages. So I'm excited to see where that technology goes.
I'm sorry. I was just going to say, working with the relationships we have with compounding houses and the various technologies that are available for the additives is a big deal. Also, I remember we were doing a tearaway sheath where we had used a siloxane in that application, and when we were looking at the tear, there was these stringers that were coming out, and we determined that was caused by the siloxane in this package. We were able to move to a different type of additive and get that removed. And that was just the technology that the material suppliers that we work closely with, identifying them and bringing them to the customers as well as the suppliers, at the forefront. They can come up with solutions to help us as well.
Thanks. You mentioned figuring out tolerances early in the design. And in prior experience, my own, it can be challenging. You run through the tolerance stack on paper. You try to, depending on how much time and funding you have, you try to prototype it and test it, but working with plastics can be very capital intensive. It's manufacturing dependent how these things turn out. So just wondering what advice you might have for how to think about the best way to approach tolerancing early stage in the design process.
Sure. So for my experiences, it is good, like you said, to kind of draw it out first, design it, and then take a look at what those tolerances are. And then, reiterating fit, form, function, what really needs to be there? Like, why does this have to be plus or minus half a thousandths? Why does this wall have to be plus or minus 25 thousandths? So just different approaches like that, and just understanding what the end goal is from the beginning. Just trying to figure out exactly how you want to make your inside, your liner part. How thick do you want that wall to be is very important, because that's going to influence the braid over the top of it, as well as the second layer going over the top of that, and there could be multiple other tie layers in between. So understanding the stack ups and what the requirement is for your French size, I think that is very important to collaborate on first. So if that kind of helps.
And software, right?
Say again?
Software.
Software helps. There are some really good simulators out there. We do have some proprietary, catheter software out of our Charlotte facility, and we would absolutely welcome a challenge to show you what we think it would look like, and predict some of these problems early on. So simulations are good, I think.
And I think, one thing we always joke about in the tubing industry is, the customers want an ID bigger than the OD. And that's where tolerancing comes in, because sometimes that's what they're drawing. And so when we do take a look at it, there's so many factors involved in it, because you got a tube drawing with tolerances. I mean, we have no way to know whether that's going to be good or bad for the application, because we don't see how it interacts with the other components unless they share that with us on the front end.
Or we're working on the full catheter.
Yes, but in addition to that, really performing a gauge R&R. I mean, how are we measuring it versus the customer to make sure that we're not, losing some of that tolerance range just by measuring it differently than they are. So there are a lot of factors involved with it that, I just usually hand over to the engineering team and let them do it.
Once a week, right? If we can get an ID bigger than an OD.
Yeah, pretty much.
We've got another question right here.
Hi, good afternoon. I love that you said that it should not be treated just like a tube, and it's a much more complex system. But in terms of, say, performance polymers like PBAX, pellethane versus PVCs, do the design requirements change drastically, or the complexity changes when it's a PVC tubing versus PBAX, pellethane?
Yes. I believe that your TPUs and your PBAXs can be a little bit harder of a material to run and manufacture, depending on what the additives are. PVC obviously is a cheaper material. Usually you'll see larger tolerances with PVC. But when you have a device that needs to be a long-term implantable or something implantable grade, I believe that's where pellethane or polyurethanes kind of take over in that sense. And they all have different drawdowns. They all have different design points for your tooling. And I think taking those into consideration will help, define and pick your materials as well. So like fit, form, function, what does it need to do? And that will help you define your materials.
Another thing is the fact that PVC, when we talk about it, it's flexible PVC. It's a compound. You're going to have a dozen or more ingredients in that versus some of these other materials that are reactor-borne. So you get a consistency there that you don't see with the flex PVC lot to lot. And it's produced the same way every time, regardless of what your ramp-up is. Whereas with flex PVC, it might be made on one piece of equipment, early stages where you're only getting a couple hundred, maybe 400 pounds at a time, versus when you're buying, thousands of pounds at a time or a truckload. So you can see it change through the ramp up, and it has to be addressed from our perspective on a process. Versus when you're dealing with like a PBAX, you don't see that same thing.
I think we've got time for at least one more question, probably. Here we go.
Hi. Are you seeing any of your customers transition away from barium sulfate? And if so, what are some substitute materials or additives would you recommend?
Yeah, I mean, I haven't really seen a big push away from barium sulfate. Really, it's just, what are they putting it in at 20, 30, 40%? What do they need? But there are times when someone will use something different, like a tungsten in place of the barium sulfate. And of course, tungsten has a much higher specific gravity. So volume-wise, it's a different loading, and it changes the performance and how you can do small diameter thin wall extrusions. And from a consistency standpoint, because of the higher specific gravity, it allows it to be more specific. But I haven't seen anything with anybody moving away or being a push in that direction. Is that something that you've seen?
I haven't seen it, but we've seen different, provider feedback, patient feedback, that there's been complications with particular devices due to the variants. You're attributing it to the variants.
Okay, yeah, and there's different grades of barium sulfate too, but if we did see that, there are alternatives that we'd be able to look at and be able to provide, compounds that include that.
Yeah, I've seen bismuth subcarbonate also as an additive that's gone away from that as well. And to Joe's point with tungsten, you have to watch how much tungsten you actually put in your material because, you have tooling that you can ruin because the tungsten's metal. So if you have like a 90% load, that's a problem. And also 90% is going to show up anywhere. So I think 70%, 80% tungsten loads are about your maximum. Anywhere other between that, but you have to remember that tungsten is incredibly expensive. I think the last time I got a quote on tungsten, it was $348 a pound, and barium sulfate or bismuth subcarbonate's about $30 to $50 a pound. So it's all, that price point is important. So we have seen a lot of transitions to the tungsten marker bands. So, saving some money, making one tube at a 48-inch length be cut into marker bands has helped as well for that. So, but yeah, there's still a lot of barium. That's a common use, and so we still see it a lot. But I try to stay away from 40%. I think 20 and 30 is where I try to keep it. 40%, it'll have an effect on manufacturing, and so that's.
Yeah, no, it comes down to what opacity are you trying to achieve?
Correct.
And like you see, it was less than a year ago, tungsten was $80 a pound, and now it's $300. Yeah, I mean,
It's all about price point, really.
All right, well, thanks everybody for the questions. Thank you for your expertise, and Aptyx, like I said, super responsive. So if you do have any questions after this, reach out to the team. They'll get back to you. Beth, any closing thoughts?
Just thank you all for joining us, and yes, reach out anytime. We're always here to help.